So the presentation here is entitled Waves to Probe, to See, and to Measure. And there will be one equation, but only one, and you already know it. The rest of it will be movie, and I will explain as possible some complex things about waves, but I will try to only show the simple side of it. So I'm Stefan Catheline, and I've been working, so I'm in Lyon at INSERM, Institut National de la Santé et de la Recherche Médicale, but I've been working among seismologists here in Grenoble during 5 years, and also in 2 physical labs here. So the first wave I would like to show you is seisms. So this is how it looks like when we are inside. Yeah, it's working. So here we are in Kobe in 1995, and there was a magnitude earthquake, so a seisms, magnitude 7.3, and we can see here the 2 guys who have heard something and that are now quite shaken. But nothing bad happens here. I cannot go back exactly where I want. But at one point, you can see here that they're going to take a look outside, both together at the same time. Right here, it is because when there is an earthquake, there is a lot of different waves. One of them is a primary wave that arrives first, and we can use that, and this is used in Japan, to stop the power, to stop the train and to save life. So this is the first arrival wave. It's not dangerous. You just hear it. You hear a sound, and then there are the waves that shake everything. And among those waves that are dangerous, there are some poetic love wave, but these are the waves that are destructive there. So where does it come from? Well, this is explained by plate tectonics. Everything is in the title here. So the plate tectonics is responsible for the seasons, and here we have a representation of the Earth 300 million years ago, and you can see that all the continents were together. There was a supercontinent called the Pangée, and the guy who discovered that is Alfred Wegener. And then, because of the continent drift, well, there is a change. The continents are moving with respect to each other, and we can see, for example, Africa, which is, and here America, which are moving apart here. Europe is there, and then this is what we call the plate tectonics, and where the plates encounter each other, there are friction, and this explains the seisms. Before the Pangée, the continents were apart, and there was another supercontinent called the Rodinia 750 million years ago, and before we think that there was again another one, the Columbia. So this is the plate tectonics was discovered by Alfred Wegener in 1912, and it took him 50 years to convince people, geophysicists, that this was true. 50 years, and this girl was important because she discovered, thanks to sonar system, I will come back on the sonar in a moment, she discovered that in the ocean there was dorsals, which mean mountain, under the water. And again, she discovered that with sonars in 1950, and it took her 10 years to convince people around her that this was really the limit of plate that was discussed by Alfred Wegener in 1912. But nobody wanted to believe her. She was a young woman, and her boss, Bruce Eason, took 10 years to believe her. And then he asked a guy, Commandant Cousteau, to take a look with a submarine to see if there is mountains there, and he could see it. So then Bruce Eason started to believe her, and then he presented her work, but without her. So it took her at least 10 additional years to be recognized for this discovery, which was really a big argument for the plate drift. Mary Tharp. So a word for sonar, because this is highly related to medical imaging. Sonar here, it can be explained like that. We have a boat here, and on top of the boat here we have antenna that send electromagnetic pulse and receive electromagnetic pulse, and we have a radar which looks like that, and when there's an helicopter that is coming around, we can see it on this radar. So this is something that we can see in the movie, for example. And in the water, there is also something like that, made for ultrasound, that send pulse ultrasonic waves, and which looks like that. So it looks exactly like radar, but it does not work with electromagnetic wave, but with acoustic wave. And this is the sonar. And the sonar is important for me because it is the ancestor of ultrasound system. So this is how Mary Thorpe discovered the mountain under the water with a sonar. That she was not allowed to go on the sea at that time. So what we can extract from seisms, and this is true for any wave, is the information that it contains. So it propagates on the surface, but not only. It gets inside the Earth, and what we know about the structures of the Earth come from the seisms. So they are very important for us to understand our planet, and the fact that there's an inner core, a solid one, an outer core which is liquid, and a viscoelastic mantle, and the fact that we are living on a teeny crust that is only 30 kilometers in average, is the result of the seisms and the analysis of the seisms by geophysicists, by seismologists. So here the crust is only 30 kilometers. It has to be compared to the radius of the Earth, which is 6,400 kilometers. So it's very small. We are only on the surface, 30 kilometers for the crust. And the biggest hole that we can dig are only 12 kilometers, something like that. So we don't know at all the structures of the Earth thanks to a hole. It's really because we are using seisms to do that. And we can do exactly the same thing for our sun. The structures of the sun is obtained thanks to helioseismology. So for helioseismology, we don't put geophones on the surface, of course, we cannot. But if we observe the light emitted by the sun, there is teeny change in their color. And we use the Doppler effect in order to measure on each point of the surface the motion due to sunquake. And then from the seisms at the surface of the sun, we are able to reconstruct the inner structures of the sun. So this is helioseismology. And this is how we can probe with seismic wave. Now I'm going to change the size, and we are going to take a look at medical imaging in order to use wave again, but to see inside the human body. So we are at the scale now of a human body, and if you go to clinics, there is three main medical imaging. I will start by this one. It's called the scanner, and most of the time we are talking with the scanner of X-ray. Sometimes we call also ultrasound scanner, for example, but scanner should be X-ray scanner. And it was the first one in clinics. It looks like that. It's a tube, and we are inside. And X-ray are sent on one side, and on the other side we detect it. And during its travel, the X-ray is absorbed, and we measure the absorption of the X-ray. And this is how we can get an image like that, where the absorption is much more important in bones than in soft tissues. So we can clearly see here, for example, the spine. Here we can recognize the ribs, here the hips. So we put in white what is more absorbed, and in black what is not absorbed. X-ray were discovered by Röntgen in 1895, and he won a new prize at the time called the Nobel Prize. He was the first one to get it in 1901. Röntgen, he discovered the X-ray. X-ray happens to be an electromagnetic wave, just like light. The other medical imaging that we can have is MRI, magnetic resonance imaging. And you can see here again a tunnel, so it's not as easy to see the difference between the two here. And in MRI, this tunnel is meant to create a big magnetic field, 7 Tesla for the most important one. And then inside we put an antenna here that can send and receive radio wave. So again, we are talking about electromagnetic wave. And then with that, with this pulse, we are able to count the number of spin, of proton, of hydrogen, of water. So to make things simpler, we can count the concentration, we can count the number of water molecule, and at the end we represent an image in gray like that, which is the concentration of water. So this is how the MRI is working. MRI is working with electromagnetic wave, and we can cite here James Maxwell. He put the mathematics of electromagnetic wave in 1865. And electromagnetic wave, again, is the X-ray or part of electromagnetic wave. So we have two medical imaging systems that uses electromagnetic wave. The last one I want to present here, and it's the third important one, maybe the most used, in fact, by physicians because it's very inexpensive, are ultrasound. So this is a totally different principle. This time we're going to send ultrasound pulse from this medical transducer array, just like sonar. And then the pulse will be reflected back to the same probe, and we are able, from the reflection, from the echo, this is where the name echography is coming from, we are able to reconstruct, like that, a baby inside the belly of his mother. So here it's a fetus at 12 weeks, and we can perfectly see here the face and the structures inside, the brain and the spine, which is very soft at this level here, at this age. And we can see different things inside the ultrasound, which are echoes, which all of this part send echoes back to the probe, and we are able to make this image out of it. This wave ultrasound has not been discovered by Paul Langevin. He's not the father of ultrasound nor sound. Paul Langevin discovered the sonar. And more precisely, in 1960, it was in the middle of the First World War, and he was asked to do something. And at this time, the military were developing submarines. So he was asked to do something in order to make them see under the water. And he was against the war and against work. He was not in favor of military developments. So first he refused, but then Marie Curie came to see him and convince him that if he developed a sonar, it will be also used for civil application. So he said, okay, I can do that. And he accepted to use his knowledge in order to develop sonar. So he's the father of the sonar, which is the ancestor of echography. And the very first to put a human body in front of a sonar are two brothers after the Second World War, two Austrian brothers, the Dussig brothers, and then they discovered ultrasound system, but it was the same thing, exactly the same thing, the same principle as the sonar. So I put here Paul Langevin. And Paul Langevin was in the good place because he was in the school where the master he had was Pierre Curie. So he's not as famous as his wife. His wife was Marie Curie, and Marie Curie had 2 Nobel Prizes, Pierre Curie had only one for the discovery of the radioactivity with Marie Curie. But Pierre Curie also discovered piezoelectricity of quartz, and this is exactly what is used here. The probe that sends and receives ultrasound is made of piezoelectric quartz, which was discovered by Pierre Curie, and he was the student of Pierre Curie. So Paul Langevin had the idea to use that to emit and receive ultrasound, and this was the big idea in order to develop sonar. So he developed sonar, and after the war, he continued to work for civil sonar, and only civil sonar. Okay, this is all what I wanted to say about waves in medicine. Now I would like to show you that there is other kind of waves. So here we have, I've been talking about electromagnetic wave for these two systems here, and ultrasound. It's like sound, like seisms. It is mechanical wave. And in our everyday life, we only encountered these two waves. There's no other one. Say that we are talking about waves in the ocean. This is mechanical wave. Microwave in the oven are electromagnetic wave there. And there's no other one. In physics, we know two other ones. The first one is the one that is used in electron microscopy. So as you can see here, it's no more related to human body. We have the head of an ant here. And this microscope is using matter wave described by quantum mechanics. And matter wave were discovered by Louis de Broglie in 1923. So I should say a word about light. So light before Newton was thought to be made of particles. And then in 1810 around, Thomas Young discovered with an experiment, the double slit experiment, that when he sent light in two slits, after the two slits, the light is, well, there are some points after the two slits that are bright or dark, which means that when we add two light, it can give light or it can give nothing. So this is typical of interference of waves, and from this date, from the Thomas Young experiment, then we discovered that light was a waves and not made of particles. And it was true up to James Maxwell, who discovered the propagation wave equation for electromagnetism, which is light. Part of light is part of an electromagnetic wave, and then Albert Einstein came, and Albert Einstein said that, in fact, light is dual. It means that it is, at the same time, a wave and a particle that he called a photon. So if to a wave we can have a particle, a photon, Louis de Broglie had the reverse idea. If we have a particle, say an electron, here this is electron microscopy, then we can have a wave, and this was the beginning of the matter wave, which has nothing to do with mechanical wave nor electromagnetic wave. So it's a third wave. And with this kind of wave, we can have a resolution much better than optics. So here, it's not that fantastic. It's the head of an ant. I think that with light, we could do, and a good microscope, we could get something like that. But we can really go very high in precision, and we can go 1,000 times better than with light. So this is matter wave by Louis de Broglie. The last wave that we know in physics was experimentally shown recently in 2015, and it was discovered 100 years ago by Albert Einstein in this theory of general relativity, and it is gravitational wave. So gravitational wave, you know that, well, it's not easy, but in space is not nothing. Space is made of a space-time manifold, a kind of membrane, and if we have two masses that are spinning around, say two black holes, when they are going to collapse, they are going to make a wave on this space-time manifold. This is the gravitational wave. And this was detected by huge interferometer like that. So it's a laser that goes 1 kilometer back and forth in this direction, in this direction. We make interference here, and we are able to see teeny change made by those gravitational waves. It was done in 2015. So now let's talk about problem in physics. So I've shown that here we have 3 kind of waves: electromagnetic here, mechanical wave here, ultrasound, sound, and here matter wave. This is all described by the standard model, which is not a very satisfying physical theory because it needs at least 26 constant, arbitrary constant to work. So it's not very satisfying. General relativity is much more coherent, and it describes the gravitational waves here. And today, the physicists are trying to merge these 2 theories that are incompatible. So this one describes what is very big, planets, stars, and this one describes what is small, our scale. All this theory comes from these guys. So this is a 27 Solvay conference, and you might recognize this guy. He's Albert Einstein, and this is why I put this equation. I told you that you knew this one. So E equal mc squared. Even if if we don't understand it, we have the feeling that this represents all the physics, and this is true. It's a very, very famous equation here, and I'm mentioning that because on the side of Albert Einstein, there is Paul Langevin, this guy with this fantastic mustache here, and he's not very well known to have worked on relativity, but he discovered E equal mc squared exactly at the same time as Albert Einstein. And he was teaching that at school, at ESPCI in Paris. And one day, one of his students came and said, Master, there is, at the time they were calling Master. My students never call me Master, they call me Stefan. But at that time, they were saying, Master, there is a guy who published your equation. He was talking about E equal mc squared. And Paul Langevin said, oh, his demonstration cannot be as general as mine, but he was wrong. So he never get published for E equal mc squared, but Einstein after recognized that this equation should have been called the Einstein-Langevin equation. I'm going to present you some other guy because it's worthy. So here, the only woman here is Marie Curie, just there. I would like also to introduce you some of these guys that you might know for different reasons. This guy here invented strange things with a cat, is at the same time living and dead. So this is Erwin Schrödinger, and the Schrödinger cat is quite famous to be at the same time dead and alive, but nothing to do with zombie. So this is another guy that you might know because there is a series called Breaking Bad, and in Breaking Bad there's a physics teacher who made drugs, sell drugs, and he called himself Heisenberg. So this is the true Heisenberg here. So for those of you who know a little bit more in science and physics, Paul Dirac, he is famous for Dirac function. This guy invented the spin. His name I forgot. He's somewhere there.
Pauli.
Pauli, exactly. Pauli is there. Niels Bohr is here. Planck, is famous for his constant. He's there. So all these guys are very famous, and they're 29. 17 has the Nobel Prize. And for those of them who are sitting here, they all have the Nobel Prize except Paul Langevin. He got nominated 15 times. So it's terrible. Okay. So now I'm going to go to my demo. I came with a demo to show you how waves can be used for other application. But first, I would like to show you a movie in order to explain a little bit, although I won't get into the details, what I'm doing. So this is a pool where we send an object here. So we can guess that when we send that in water, we create waves around. So this is what we are seeing here, this circle. And all in the border of the pool here, we have detectors. And each detectors of waves is connected to an electronic memory. So what we're going to do here in a second step that we're seeing here is to use the same detector but as emitter. And we are going to do a time reversal experiment, which means that we send first the waves that arrived at the end, and we send at the end the waves that arrived first. We read the memory in reverse order. So this is what we call a time reversal experiment. So this pool is meant to test the mechanical platform, the offshore mechanical platform for oil. So this is all paid by the Brazilian petroleum. And we put the offshore platform here, and we send waves to test the mechanical resistance. And Nicolas Pérez, when he saw this, he said, oh, we can conduct a time reversal experiment that we are seeing at the moment in real time. So at one point, you will see that the waves reorganize themselves and recreate a circle. It's not the movie that is going in the other way around. And this circle is exactly focused where we send the object, and nothing will show off the water here. And then, for conservation of energy reason, we can see again the waves that are coming from this point here. So this is a time reversal experiment. When we have an object, if we measure the waves in a closed cavity, we know exactly how to refocus back to the source. So the waves have conduct information about the source location. This is what I'm going to use in my experiment. I will conduct the time reversal experiment, but numerically with MATLAB. So this is the part where I sweat because it's a demo, so we never know if it's really going to work, but usually it works. All right, so let's go. Okay, I should have presented you what I'm going to use, so sorry. Oops. So I use MATLAB. MATLAB is meant to control the device, the electronic device, and put the curve on the screen here. So I'm using two microphones that are here. Two microphones that I'm going to put on this table, this wooden table. And in order to hear the sound that I'm going to create with this table, I'm going to put something on top of each of the microphones so they are in good contact with the table. These two microphones are connected to an external sound card here because I don't have it on my computer, and the sound card is connected to my computer. So now, if everything's okay, the computer should hear the sound that I'm going to create now. This is it. So something happens here. You can see that there is a line, a green one. There's two of them, in fact. It's difficult to see, but I have a green line and a blue line because I have two signal, electric signal that is coming inside my computer. This is time, and this represents the sound that I've created with my fingers. So first there was nothing, and when I knock up, you can hear the sound and represent it as function of time. So we're going to use that, and if I knock again on another point here, you can see almost that the sound is different. So each point of the table has its own acoustic signature. So I'm going to use that in order to, here I put a paper with different cross, and I'm going to put in the memory of the system the sound made by this impact. Okay. All right, so he's saying, I put in my memory the new reference number 1, number 2, 3, right, 4, come on, yeah, well, all right. Okay, let's try it here. It's incredible. Right, let's put it here. 4. Is deaf. All right. Now I have 5 reference. Now, if I knock on the 5 points, so I mixed a little bit. This is the point number 1. This is the point number 2, 3, 4, 5. All right. Let's try to the 6th point, and we're going to start the demo. All right. So if I knock on point number 6, he's going to open a window. So some additional manipulation here. Right. All right. So now, from the 6 point I have on my table, I can control the sound played by this software here. So when I knock on point number 1, it recognizes point number 1, and he knows that he has to play the song. So we can barely hear it. All right. When I knock on point number 1 again, it pauses. When I play with 1 and I knock on point number 2, I stop the song. All right. When I knock on point number 3, it can change. So here we are in the first one there. Attitude dance. So I'm going to try the other one to see if it's better. No, it's not better. So I can switch, knocking with point number 3. I can come back with point number 4, if you can hear it. But apparently here, oh yeah, no, it's here. I changed 6. Not at all. Sorry, so pause. Ah, no. Okay, right. You understand the idea, and this is not what I wanted to show. All right.
Because the speakers are on the same table.
Because what?
The speakers are also on the same table.
I accept this, apologize. But I'm afraid I usually this is what I do, and it's perfectly working like that. So this is what I wanted to show you at the end. Of course, this table became more or less a remote control, which can be done for any kind of object. All what we want from this object is that it conducts sound, which is true for any object. So it can be a wall, it can be shoes. Any object can become a remote control with this approach. But what I wanted to do is not this. I wanted to measure the elasticity of this table. So this is what I'm going to do right now. And hopefully it will work until the end. So in order to do that, I'm going again to use time reversal. I've forgotten to mention that here. In order to recognize which point was impacted, I computed the time reversal within MATLAB, and I was able to see where is the waves converging among the 6 points I had here. So now we are going to reconstruct the refocalization of time reversal, and I'm going to knock on 10 consecutive points distanced with a distance of 1 centimeter. So I'm going to reconstruct the table wave. So let's go. Haut les cœurs. All right, so demo number 2. How can we measure the elasticity of this table? So let's go. Do you hear me? Yes. All right. So point number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, wait, it's not 11 at all. All right. Anyway, I continue. All right. So it worked, more or less. But no, more or less, more than less. DQ. All right, this is the result. So I focused the waves in the center of the 10 points that I've just measured. So now what we're seeing, a waves is a sinusoid, something that do like that in time and space. So here we are seeing an arch of the sinusoid, but we see only one of the arch. So from the size here of this arch of sinusoid, I can guess the size of the wave, the wavelength. So this is what is measured here, and the wavelength here, when I knock on the table, is 35 centimeters. So it's something like that. When I knock, like here, the waves is this size. If I know the wavelength here, I know the frequency contained because I have this measurement here that tells me something. This is time, so I can know the frequency of my wave. If I know wavelength and frequency, I can measure something very important for us, is the velocity of the wave. And the velocity here is 350 meters per second. So it's not that different as the speed of acoustic wave of sound, 340 meters per second. And then, when I know the velocity of the waves, it's important because it's related to its stiffness. The stiffer the object, the faster the wave. So here, from the velocity, I can deduce the elasticity in megapascal, 126 megapascal. So what is it useful to measure the elasticity of a table? I'm afraid the answer is there is no at all. It's just a demo. It's not useful to anything. But we can do exactly the same thing for medical imaging. And this is interesting because we can measure the elasticity of soft tissues. So this is the end of my presentation and my last slide. And this is what we're seeing here. So let me introduce you. So here we have standard medical imaging here that I was talking about. So this is 2 ultrasound image of the liver here, human liver, the human thyroid. In black and white, it's standard imaging, by the way. This is MRI, again, the brain, which is visible here. This is optics. So we can see here a part of the eye of a sleeping rat. So this is the cornea, and this is the white part of the eye called the sclera. And this is a single cell called the novocyte. And from this, we can use exactly the same kind of approach that I've shown here on the table to measure the elasticity of the table in order to measure the elasticity of tissues. And we are able to measure the elasticity of the liver, which is this part here. So we can see that it's softer than these layers and softer. When it's red, it's hard, stiff. Here, the same thing happens with thyroid. With MRI, we can do the same thing and take a look at the part of the brain which is a little bit harder. The same thing for the eye here and the single cell. And we can apply that also to the US, for example, in seismology. And then we know that the West Coast is softer than the East Coast, something like that. I don't know if it's this way or the other way around. Yeah, so it's softer, yeah, no doubt. Okay, so this is I will end on this, on different application of waves in seismology and in medical imaging. Thank you for your attention. If you have any questions.